Okay, we're back with a lot of space here, but you'll notice that I've put something on the screen over here, and this should look kind of familiar because this is pretty much exactly the same diagram that we had up here for the previous lecture. And we're going to say a few things about this and use this to develop the idea of the differential. So I'll come back and I'll be working in terms of this diagram. So let's note that our Taylor polynomial, if you'll recall, was that Taylor polynomial was f of x bar plus, and I'm going to write this as just L of delta x for the moment. And so this was the Taylor polynomial where this was f. In fact, let me add on here the remainder term so that the equation is actually correct. Okay, so this is not the Taylor polynomial. This is f of x is the Taylor polynomial, which is just these two terms plus the remainder term. And I've left off the subscript 1 here, but this, of course, is the remainder term for this is all the first degree Taylor polynomial, the linear Taylor polynomial. And, of course, note that this is f of x bar plus delta x. And so let's note that L of delta x was this linear function that I've drawn in orange over here. I think I drew it in orange in our previous lecture. It's this linear function, and it's a pure linear function in that it's homogeneous. That is, when delta x is 0, it's 0. So it's not just an affine function. It's a pure linear function. And then, since it's a linear function, it has to have the form a times delta x, since it's a linear real function. So it has to have the form a delta x. So let's write that in over here, a delta x plus r delta x, the remainder term. And let's write that this is f of x bar plus f prime at x bar, delta x plus r delta x. So that's what we did last time. We figured out that this coefficient here had to be the derivative if we wanted this to be a good approximation to f of x. And so let me write now, when we write this, we mean this is a good approximation of this, or this is approximately this thing over here. So I'm going to leave off the remainder term, and I could have taken this off everywhere here and put the little wavy equals sign, and then our f of x, or f of x bar plus delta x, is approximately f of x bar plus the linear function here. And so when we go over here, that's telling me that f of x at this x down here is approximately f of x bar, which is this, plus this linear function evaluated at delta x. So that means it's approximately this number here. The exact correct f of x bar plus delta x, is this level here on the y-axis, but it's approximately this level here, f of x bar plus L of delta x, f of x bar plus L of delta x, which is this linear function here. And so let me do this. Let me leave a little space because I may want to come back and put something down here. Didn't leave myself a lot of space. And so now what I want to focus completely on is I want to focus on just the change in y, right? So that's just f of x In fact, let's even say it's, well, I'll write it as f of x instead of writing it this way here, minus f of x bar. So that's exactly what I've written as delta y over here. It's how much the y variable, how much the value of f has changed when I move from x bar to x bar plus delta x, when I move by the amount delta x. And so that is, so I'm just going to rewrite things here, but I'm going to leave off the f of x bar. So we have that delta y is equal to L of delta x plus R of delta x, and that's equal to A times delta x plus R of delta x, and that's equal to f prime at x bar delta x. And so now I'm actually going to take the remainder term off in both places, and I'm just going to put in here wavy equal sign. So this gives me a good approximation to delta y, so long as delta x is sufficiently small, and how small just depends on the situation at hand. As we saw last time, that delta x could be, fairly large. I think delta x, we looked at a delta x that was equal to x bar. It was 1, I believe, last time, if I'm not mistaken, when we looked at, well, that was a situation where we looked at e, I think we looked at the exponential function e to the x, so I think we had x bar equal to 0 and delta x was 1. So what I said there was not quite right. So, so this gives us a good approximation of the change in y, and this is and I'll even put a little colon over here because I'm defining now something called the differential as a function of delta x, and we typically write an x bar down there. And so we call the linear function here, we call this linear function where we kind of suppress f of x bar, the value of f here. We call this linear function the differential function, or the differential of f at x bar. So let's actually write that down here. This is the differential of f at x bar, and it's, well, it's often called a total differential, but here I think in this when n is 1, because everything we've done here, of course, is for real functions. And so now let's move ahead to functions defined on Rn. And so now I need to convert everything here to work for functions defined on Rn. And so we're still going to use the same notation. We're still going to call it the differential of f at x bar. But of course, what I want to do here is I want to replace f prime. So delta x now is a vector. So let's actually make that clear, that delta x here is now in Rn. So what I want to do here is I want to put the gradient in here. So let's take this off and let's replace it with the gradient. And let me even put that in this color here. So this is the gradient of f at x bar. And of course, Up here, we have the same thing going on. Here we have this is an Rn, so this A here has to be a vector, A1 to AN, and it is the vector, which is the gradient. Linear function has to be a vector of coefficients times the vector of variables, delta x's here. So it's still the case that delta y is in R, and y is still just a real number, but the x's, they're in Rn, the delta x's are in Rn, so the differential of f at x bar, this item here, is now the dot product of the gradient of f evaluated at x bar, dot product with delta x. And so, of course, we can write that in more extensively as the partial of f with respect to x1. And of course, this is evaluated at x bar, but I'm going to suppress that and leave that off, times delta x1. Well, we'll put the second one in here too. So this linear function of the delta x's is what we call the differential. And here, this is sometimes called the total differential. Some people even call it the total derivative. I think that's probably not very common, but I have seen it. A lot of people call this the total differential. I'm not really clear why they call it the total differential, because there isn't some other differential that's non-total. So I don't particularly like that terminology. It's the differential, the linear function that gives us the best approximation to the change that takes place. The linear function that gives us the best approximation not to f of x, but to f of x minus f of x bar. So this shows up a lot in economics. So we'll use this a lot, and we'll use it a fair amount in the rest of the course here. Let me see here. I think the only thing that remains to be done, and to notice that, of course, I use this picture over here. I've referred to it very little now. I use the picture over here just to remind ourselves how things work in when n is 1, when we have a real function. And this is very useful as well for seeing how this differential works when n is 1. But of course, as soon as we go to Rn, then we have kind of an analog of this in Rn, but this isn't, of course, any longer just the right picture. I think that I left out something that I wanted to do earlier. And so let me actually, I'll come back and do that at the end, okay, because I want to continue with the idea here. And then I'm going to come back and add something that I think I left out, and I can't tell for sure because it's not on the screen anymore. So what I want to do is just apply the idea of the differential in exactly the way that, the kind of way that we often do in economics with a function that we often actually see in economics. So this is an example. I'm not going to be using the graph up here. And in fact, because of that, let me take the graph off here so we've got a little more space to use for this example. And then we'll come back and we'll do an example, and we'll also add that little bit that I think I left out. Okay? Okay, so let's now do an example, a very specific functional form example where we use the differential. And so let's have f be defined on R2, and let's let this be 2 log x1 plus log x2. And so this is actually going to be the natural log, and in fact, whenever I write the log function, it's going to be the natural log unless I say differently, okay? Which is unusual enough that it probably won't even happen, that we'll use something other than the natural log. Let's note, first of all, what are the partial derivatives? So let's just write this down as the gradient of f at x, at any x, okay? And so that's going to be the vector of partial derivatives. And there are only two variables. We're in R2. So the first partial derivative is the derivative of the log function is 1 over x. So this is going to be 2 times 1 over x1. So this is going to be 2 over x1. And this is going to be 1 over x2. So this is particularly simple because it's separable into the sum of a function of the first variable and a function of the second variable. And by the way, you recall a few moments ago, I said that if we have a function, let's say on Rn, which is composed of other functions that we know are continuously differentiable, composed of those functions by being the sum of such functions or the product of such functions. This is an example of that. So this is composed of functions, in this case, real functions that are getting added together to give us our function here, a function of x1 and another function of x2. Both of these are known to be continuously different analytic functions. They're continuously differentiable in every order. And so that means this is continuously differentiable, not just of order 1, which is all we're using here and all we're using over here, but actually continuously differentiable of all orders. So this is our gradient as a function of x, and you can see that the x's are in here. And so let's now say at x bar equals 1, 1, and I'm using something where the numbers are all real simple. At x bar equals 1, 1 in the domain. Maybe even go down here and draw a picture of what's going on. x2, x1. So this is x bar. And I have actually, let's even draw in the level curve. We've got some level curve going through here that looks about, well, yeah, so I think the level curve would look about like that, if I'm not mistaken. And so what I want to do, let's first evaluate the function at x bar, because that's easy. So I have f of x bar, that's going to be 2 times the log of 1, which is 0. Log of 1 is 0. Here, log of 1 is 0. So this is going to be just 0. So this is 0. And let's, I don't think there's anything more I need to do there. And let's now say for delta x equals, let's say 0.1, 0.1. So I'm now moving in the direction, in this direction, but I'm only moving a little ways. I'm only moving to about here. So this is x bar plus delta x. And so for delta x equals 0.1 and 0.1, I'm now going to apply the differential. So I have df x bar of delta x is the first partial derivative at x bar times delta x1. Well, what's the first partial derivative at x bar 1? The first partial derivative is 2 over x1. And if x bar is 1, 1, then that's a 1 in the denominator. So this is, let's even write it as 2 over 1 times delta x1, and delta x1 is 0.1, plus the second partial derivative evaluated at x bar, but x2 bar is also 1. So this is 1 over 1. And I've got 0.1 in here again, real simple. I used numbers that we're going to work out without a lot of trouble here. So this is 2, well, let's just note that it's 0.2, 2 times 0.1, plus 0.1, that's 0.3. Not 3, 0.3. So this is 0.3. Well, what I perhaps should have done was to look at, let's look at f of, now let's look at f, I probably should have written this down first, f of x bar plus delta x, that's going to be f of 1.1, which is 2 log 1.1 plus log 1.1. That happens to be, well, you can see it's 3 times the log of 1.1, and that happens to be 3 times, I believe it is 0.0953, and some more stuff, of course. So that is 3 times this is 0.2859, it appears to be 0.27 plus 159, 0.2859, and so that's not that far from 0.3. So I have the remainder or error associated with this is f at x bar plus delta x, this number, minus 0.3, which is minus it appears to be 0.0141, and then some other stuff. So I've used the differential. So I don't know. I mean, I know log 1.1 because I looked it up, or I used a calculator to get this, right? But I did not know offhand. I mean, you might have said, how does he do that in his head? 0.0953 for log 1.1. I did not know that. So, I stuck it in a calculator and I got 0.0953. I can multiply that by 3 in my head pretty easily. But in general, I don't know what this is, and I'm trying to approximate it with the differential. And so I take my differential. That part is easy, right? It's easy because I have the log of 1, that's 0, and that gives me f of x bar, which is 0, and I can approximate delta y as a function of delta x, delta y as a function of delta x, approximately using the differential. And so I use the differential. In fact, let's even put over here, delta y is going to be approximately the value of the differential at our delta x, which is a vector. And so that's easy to get. I just take these simple partial derivatives, multiply them by the delta x components, 0.3, easy, and it turns out the approximation's pretty good. We're off by 1/100th for a movement of 1/10 in each direction here. Now, if you do this for a larger delta x, you're going to find that your error is a little bit bigger. In fact, if you do this for both components of delta x equal, let's say, to a half, so you go from the vector 1, 1 up to the vector 1.5, 1.5, and you want to estimate delta y, or ultimately, of course, f at the new x. And you do the same thing. You can do, this is really easy. This is simple as can be. But then of course you'll have to do something on the calculator to get the exact value to sort of see what this error actually was. You'll find that the error is a lot bigger. The error here is on the order of 1/4, something like that, if you do that. But again, doing the approximation is really easy, and that's the point of doing this with the differential. The differential also is very useful theoretically, not just for doing these approximations, but it's very useful theoretically, which we will see, I think, in the next lecture. In fact, probably several times in the coming lectures, we're going to probably see this differential being used. So that, I would say that's it for this lecture, but you remember I said that I left something out. And so let me put that down here. So this is unrelated to this stuff here, but when I was talking about the second order partial derivatives, let's actually write in a typical second order partial derivative, and even put in that it's evaluated at x bar. The matrix, remember I said there are going to be n squared of these second order partials because we're in Rn, so there's n components and n components here, n squared combinations. So there are n squared, so this, I can make up a matrix consisting of all the second partial derivatives, and so the ijth term of the matrix, or element of the matrix, is just this second order partial for I and j. So this is going to be an n by n matrix if F is defined on Rn. This is the Hessian matrix, and I write this typically as H at x bar. And by the way, we don't always have to have the x bars in here. So if I take the bar off, well, that didn't work too well. So let's take the bar off here. So, okay. So the second partial derivatives, of course, are functions of x. They depend on x. And so this is the Hessian, or the Hessian matrix of F at x. Or if I had x bar, then it would be at x bar. And to make sure that we know what the function is, we often write a little subscript f, so it's the Hessian matrix of F at x. It's the matrix of second order partial derivatives at x. This is also often written, probably more often written actually, as D, capital D2 sub f of x. D2 being the second derivative of f, second order partial derivatives of f. So written this way, I just like to write it as h because it's a little simpler than writing this. I often leave off the f here, and h because it's the Hessian matrix. And you'll see it written as h a lot of times, but this is more common, I think. Just not more common with me. Okay. And so one more thing we should add is a theorem here we're not going to prove, and that is if f is a C2 function, if it is a function whose second order partial derivatives all exist and are all continuous functions of x, then h of x, and I'll put the f down here, is a symmetric matrix. An important point. This just means that, of course, another way to say this would just be to say say this, for every I and j. So this actually is important. It's an important result, but we don't actually refer to it a lot because, as I said, typically we're working with functions that we know are the C2 functions, and we know the matrix is symmetric, and so we just don't make a big deal out of it. We just go ahead and assume that we have a symmetric matrix. And I should, I guess, add this is called Young's theorem. So, you know, we refer to it kind of in passing fairly often perhaps, but we don't make anything much out of it. And typically we just go ahead and assume we have a symmetric matrix because we're working with a function that actually is a C2 function. So that's it for today's lecture. And all we wanted to do here in this lecture was just to kind of develop some of the ideas of derivatives that we're mostly kind of familiar with already, but we want to just get them kind of on the table here so that we're all together going forward, because we're going to start using these ideas as soon as the very next lecture, where we're going to come back to approximation and Taylor's theorem, but Taylor's theorem when we have a function defined on Rn on Euclidean space. So that's where we'll go next time. That's it for today, and we'll see you next time.